Welcome to the part 2 of lecture 2, that is characterization of single particle. In the part 1 of this lecture, I have told about the size of a particle, what is the purpose to measure the size of a particle, and what are the different ways to define a particle size. Now in this part 2 of lecture 2, I am going to discuss the shape of a particle. For many years, particle size has been recognized as a key parameter in the development and manufacture of a wide range of pharmaceutical materials. However, in recent years and with the advent of rapid and reliable measurement technologies, particle shape has assumed a similar importance. Now, why particle shape is important, that I can demonstrate by this figure. If you consider this figure, it has two images. In images 1, the particle of very irregular shape are shown, and here particle which are shown having a similar shape. Now if I consider both these particle, it has same particle size distribution as you can see from this figure. Now this particle size distribution says that if I consider size of particle only, it behaves similarly in the process where it is used. However, it is very difficult to say this, that behavior of these two samples would be equal. Why it is so? Because both are having different shape. So what is the effect of this? Their flow and aberration characteristic would be dramatically different, but particle size data alone would not allow differentiation between them. Therefore, along with measuring the size of a particle, to identify the shape of particle is equally important. So measuring particle size alone is sometimes insufficiently sensitive to identify important but subtle differences between samples. Some batches of samples may differ by such a small amount that this difference is lost during the translation to a circle equivalent or spherical equivalent diameter. For example, consider the three shapes which are given over here. Here that I have already taken this example while discussing the size of a particle. Here if I consider this square, this triangle and this circle, both are having same circle equivalent diameter. So what is the meaning of this? That if I am having same equivalent diameter of different shape, I assume that they behave equally wherever they are used in the process. So this highlights the main disadvantage of measuring particle size only. Very different shape samples could be characterized as identical simply because they have similar projected 2D area or similar spherical equivalent volume. The particle shape often has a significant influence on final product for performance parameters such as flowability, abrasive efficiency, bioavailability, etc. So some way of characterization shape is required. Therefore, here I am going to discuss the way to define the shape and techniques to compute the shape factor for a particle. So particle can be of different shape, like it may be cubes, plates, rods, blocky, rectangle, irregular, needles, etc. So all these we are having different shape of a particle. Here we have, these are the single particle, and here due to agglomeration it acquire different shape during the process. So along with size, shape is also important. Defining particle shape. Now here basically we want to define the particle shape. So if you consider the particle shape, it can be defined. How it can be defined? How it can be computed? That is very important. However, it is very easy in comparison to defining or in comparison to measure the size of a particle, because when we equate the size of a particle to some parameter, to some property, it has, while equating this we can calculate the equivalent diameter of a particle, but how we can define the shape of it? So various aspects of particle shape are of interest, and therefore a range of descriptors has been devised to allow particle shape to be quantifiably described. No single shape descriptor would be suitable for all purposes. So shape descriptor follow some criteria. Like some criteria we have defined, based on that we have some descriptors or we have some definition of a particle shape. First criteria is intuitive. It should be consistent with the way the human mind perceives the parameter title. For example, if I am having the square shape of a smooth surface, I am having the square shape of irregular surface. So definitely I can say that their shape factor may differ because of the roughness of the surface. So how it comes from? That the way I have identified, the way I have seen the object, accordingly I can say that their shape would be slightly different, though both are having the basic same shape, that is square, but one is a square with the smooth surface, another is a square with rough surface. So that is due through intuitive we can define the descriptive. Another is normalized. It should have the value between 0 and 1, thus making interpretation and data processing easier. So whatever descriptors I am having to define a particle shape, all are falling in a range from 0 to 1, though this is not the case with the particle size. Particle size we equate to the property and then we calculate whatever would be the magnitude of it, that we say that this is the diameter. However, for shape I am sure that it should fall between 0 to 1. So that normalized is a criteria. Third criteria is sensitive. It should be sensitive to shape deviations as experiences in real world sample. Like previously I have given an example when a square is having smooth surface, when a square is having rough surface. So though both object we are having of a square shape, but I should be sensitive enough to identify that, and that should be reflected in terms of the value which falls between 0 and 1. So based on these three criteria we have different descriptors. First is we define as circularity. So circularity is basically how circular the shape is, it defines that. So which is defined based on the perimeter. Second descriptive I am having is the convexity, and this is defined based on the surface roughness. So if you see the convexity of this circular shape as well as this elliptical shape or elongated shape, both are having convexity as 1. So it is defined based on surface roughness. It has a smooth surface, it has a smooth surface, so both are having convexity equal to 1. However, when we define the circularity, depending upon the circular nature of the particle, the circularity vary, but all value will fall between 0 and 1. Third, we are having the elongation, how long the particle is. Like here, if we consider this circle, it has elongation 0, and if it is elliptical in shape, it has elongation 0.82. So this is defined based on length over width ratio. So here we have three descriptives. We are going to discuss these three descriptive in detail. First is the circularity. How the circularity is defined? It is the ratio of perimeter of a circle with the same area as the particle to the actual perimeter of a particle. So here we have to equate the perimeter of a circle of the same area as the particle to the actual perimeter of the particle. Circularity also has values in the range of 0 to 1. A perfect circle has a circularity of 1, while a very spiky or irregular object has a circularity closer to 0. Here I am having one example how to define the circularity of an irregular particle. If I am having this particle and this black section you are seeing, this is the projected area of the particle, and this green line is basically the parameter. If we consider this section, it is defined as the perimeter of the particle, and this red circle is the circle with same area as the particle. So considering this image, we have defined circularity as circle circumference divided by the perimeter of projected particle image. So if we consider this circle, obviously it has circularity as 1, but what about this particle which is having a square shape? So for square shape, I assume that its side is of 1 unit. So diameter of circle, because it is circularity is defined as circle circumference. So circle circumference, for this we have to calculate the diameter. So how we calculate the diameter? While equating the circle's area equal to the particle area. So if I am having a square shape, the particle area would be 1 only. So diameter of circle, that is square root of area of a square into 4 by r, that is it should be 1 4 by r. So 1.128 unit diameter we have found. So circularity is the circle circumference, that is pi into 1.128 divided by 4 into 1, that is the perimeter of the particle. If it is a square in shape, it has 1 into 4. So similar value appears over here. So circularity comes as 0.886. You can see the value over here. And if we see this image, we have circularity of circle 1. As it gets elongated, its circularity reduces. For circular section, for this rectangle section, circularity vary. And if you see this particular image, it does not have any effect due to roughness of particle. It has 0.47 and it has, if I consider the roughness, but due to this elongation, due to this non-circularity, the value differs, but all value will fall between 0 and 1. Now we have the convexity. The convexity is a measurement of surface roughness of a particle and is calculated by dividing the area of circle with the same area as the particle by total area. So you can see the definition, it is the area of circle with same area as the particle. So we can equate the circle area with the particle area divided by total area. So in other words, the convexity can be defined as the particle area divided by total area. How we can define the total area? That I can illustrate by this example. If you see this figure, here we have the convexities of different shape. Now if I consider this rough surface, it has convexity lesser than 1. So if I am having the smooth surface, convexity should be closer to 1 or equal to 1, and as the roughness increases, convexity reaches towards 0. In this figure, if I want to define the convexity, that is the particle projected area, that we can calculate very easily, divided by total area. So what is the total area? If I place a rubber band around this, whatever would be the area of that rubber band, that basically called as total area. So convexity is defined as the particle area divided by total area. So as surface roughness increases, the total area which is enclosed in the rubber, that will increase than the particle area itself. So that is the convexity. Next I am having elongation. Elongation is a measurement of length over width ratio and has the value in a range of 0 to 1. Elongation is a comparison between the strength of the major axis, that is length, and strength of the minor axis, that is width of the particle. So if we have elongation, how we can define the elongation? It is 1 minus width over length, in order to obey the intuitive rule, that is while seeing what should be the value of it. Like if I define the elongation, we can very well identify that I can, if the particle shape is of needle, it must have the elongation equal to 1. So shapes that are symmetrical in all axes, such as circles or squares, have a length and width of similar value, so elongation close to 0. Like in this case, we have elongation close to 0, whereas needle shaped particle have a length that is greater than their width, so elongation would be equal to 1. So the actual calculation of elongation computes the center of gravity of a particle and defines the exact position of major and minor axis. So from this figure you can say that elongation is more an indication of overall form than the surface roughness. A smooth ellipse has the similar elongation as a Spicay ellipse. So if you see all this figure, here we have, this is smooth ellipsoidal surface, here we have rough ellipsoid. So both are having same elongation value. So that is basically based on the length and width, not the surface. Here I am having three descriptives. Along with this, we can define particle shape based on different factor. The first shape is sphericity, and the factor is it based on surface area per unit volume. Second shape is specific surface ratio, that is based on surface area per unit mass. Volume shape factor, that is based on volume. So let us start with the sphericity. It is based on surface area per unit volume. So how it is defined is, it is the ratio of surface area of a spherical particle having same volume as the particle to surface area of the particle. Since the diameter of a spherical particle having same volume as the particle is dV, because now in this case we are considering volume diameter instead of simple diameter. So sphericity would be the spherical particle area divided by the surface area of the particle. So it must be noted that since sphericity compares the surface area of particle to that of equivalent spherical particle, it defines only the particle shape and is independent of the particle size. For example, if I am having a particle of 1 mm diameter or 10 mm diameter, when we equate the surface area of the particle and the equivalent surface area of a spherical, both are having same value, so that it will not affect it by the size of a particle, it completely defines the shape of the particle. Here I have shown one example to calculate the sphericity of a cylindrical particle which has length and diameter both are equal to L. This dV is defined as the diameter of spherical having same volume as the particle. So that dV would be equal to 6 V particle by pi. So that V particle is the volume of particle and 6 pi power 1 over 3 would be the dV. So if I am having cylindrical particle, both its diameter as well as length equal to L, so its volume would be pi r square L. So pi r square L can be written as pi L square by 4, because L is now equal to the diameter, into L. So pi L cube over 4 would be the total volume of the particle. 6 by pi we have taken as it is, and the power 1 over 3 we have considered. So dV we have calculated in terms of L as 1.143 into L. So we can define the sphericity as pi dV square by Sp, that is the surface area of a spherical particle of dV diameter divided by surface area of actual particle. So that pi 1.143 into L whole square, that is the surface area of a spherical particle, and this pi 1.5 L square is the surface area of cylinder where length as well as diameter are equal to L. So sphericity in this case is 0.871. So here if I am having more irregular shape, the sphericity would be close to 0. If I am having perfect sphere, the sphericity would have the value equal to 1. So here I am having some of the typical values of sphericity for depending upon different material like sand, pulverized coal dust, Raschig rings, etc. So these sphericity is defined. Whatever would be the size of this, irrespective of this, we can consider the sphericity equal to these values. So reciprocal of sphericity is commonly called the shape factor, or more precisely the surface shape factor, that is lambda s. Thus lambda s equal to 1 by phi s. Another value or another shape factor we are having is the specific surface ratio, that we denote by N. It is defined as the ratio of the specific surface, that is surface area per unit mass of the particle to the specific surface of the spherical particle of same diameter. Let the average size of the particle be d average. So obviously when I consider the spherical particle, that must have the diameter equal to d average, because here we have equated in terms of diameter. Then how we can define n is the specific surface, that is surface area of a particle per unit mass divided by the surface area of the spherical particle per unit mass. So how the surface area per unit mass of a spherical particle is defined? Like if I consider 6 by d average, that would be the surface area per unit volume, if you remember the shorter diameter definition, and when we multiplied this with the density factor, so that would be surface area per unit mass. So considering this, we can also calculate surface area of particle in terms of specific surface ratio, where rho is the density of the particle. Having the graph of log plot, which is plotted n versus d average for different material. For example, here I am having different material like quartz, pyrite, sphalerite, galena and calcite. So on this axis we have a specific surface ratio. Here I am having average particle diameter. So if I know the diameter that is shown over here, we can calculate the value of n, and then we can calculate specific surface per unit mass of a particle. So that is about the specific surface ratio. Next we have the volume shape factor, that is A. So this factor is sometimes used for calculating the volume of an irregular particle. We know that volume of a spherical particle is proportional to the cube of its diameter. Like I have shown over here, Vp is proportional to d average cube. Now once I remove this proportionality constant, this would be equal to Vp A d average cube. So that A is basically defined as volume shape factor, where A is the constant of proportionality, and for a spherical surface the value of A is pi by 6. So accordingly we can define the volume shape factor. So here I am having the summary of lecture 2, which combines the summary of part 1 and part 2 of lecture 2, that is characterization of single particle. So summary goes as: characterization, that is measurement of size and shape of a single particle, is discussed in lecture 2. Secondly, we have discussed a number of ways size of a particle is defined, which depends on controlling characteristic, and finally based on the utility, different definitions of shape of a particle is described. These are the references you can refer. So that's all for lecture 2, and thank you.